Good morning, everyone. Myself, Dr. Deepak Yadav, and I am teaching digital system design subject from the EC second year student. So, we are going through different topics in this digital system designs, and binary coded is one of the important topic that we see in this digital system design. So, binary code is basically the representation of binary bit in different coding combinations, like in gray code, in digital codes, in ASCII codes, in BCD codes, and these are the combination of 1 and 0 bits which is arranged in different manners. So, we are go through the different binary codes in this topics, and we will see how we deal with this different codes and how we convert from one code method to the another code method. So, these are the topic that we are going to cover today, that is BCD code, that is binary coded decimal, then BCD addition, how we can perform the BCD addition using BCD codes, then other decimal codes like 2421 code, 8421 code, 24 minus 2 minus 1 code, then gray code, these are the single bit changing code, then ASCII codes, then error detecting and correcting code. So, the next one is, the first one is the BCD codes. The BCD code is nothing but the binary representation of the decimal number. As you can see, this is a decimal number 0, and we can represent this decimal number 0 with the help of 4-bit digital codes, that is 0, 0, 0 and 0. So, now this 4-bit digital code is the binary representation of the decimal number 0. Similarly, for the code 0001, this is the decimal representation. This is the binary representation of the decimal number 1. So, the thing is that why we use this 4-bit code only, why we not use 3-bit code or 5-bit code? This is because we have the possible number of symbols in the decimal number is only up to the 9, and we can easily represent the number from 0 to 9 with the help of 4-bit code only. If we go to the 3-bit code, we can only represent up to 0.7, up to the number 7. When this is not sufficient in case of BCD, we need up to decimal number 9. So, for this we go for 1 bit higher number of code, that is 4, and in which this extra bit produce up to the number 8 and 9, and the other bits, that is 10, 11, 12 is not used over here, because the BCD number is only up to the 9, as you can see, and these are the equivalent binary representation of these BCD numbers. So, we can say that the decimal number is represented into the binary form with the help of binary coded decimal. Now, how we can perform the addition in the binary coded decimal numbers? So, we can easily convert any binary coded decimal, that is BCD number, into its binary in BCD equivalent, as if we have the number 185 and this is a decimal number, and if we want to convert into the binary coded decimal or BCD number, we directly write the 4-bit code equivalent of this one, that is 0, 0, 0 and 1, 4-bit equivalent code of 8, that is 1, 0, 0 and 0, and 4-bit equivalent code of 5, that is 0, 1, 0, 1. So, the total number is the binary representation of this BCD number, that is, this is represented by this. This is different from the binary representation, as you can see over here. If we want to represent the binary equivalent of this number, what we have to do? We have to divide as 185 divided by 2 up to the point where all the numbers are divided by either 2 or 1, or the remainder is written over here, which is the binary equivalent of this 185 decimal number. So, there is a vast difference between the BCD and the binary representation of any decimal number. Here we are dealing with the BCD number. So, in this way, with the help of this method, we can easily implement decimal number into the binary code. But if we perform the addition in the case of binary BCD numbers, there is a 3 different cases for which we have to deal. Like, the first case is that if we have the summation of the two BCD number is less than 9 or equal to 9, then there is no need of any correction, because BCD is easily demonstrated with the help of 4-bit number, which is maximum up to 9. So as you can see over here, this is a 4-bit number 4. This is a decimal number 4, which is represented in the 4-bit as 0100, and a 4-bit number 5, which is represented as 0101. So the sum is 1 0, 1 plus 1 0, carry 1, and this is 1. So this is 9, which we can easily implemented in the BCD. So there is no need of any correction. The result is as it is. But the second case is when the addition of the two decimal number is greater than 9. So we cannot represent the number which is greater than 9 in the BCD direct, like 10 is not represented in BCD, 11 is not represented in BCD. So the second case is when the addition of the two BCD number, for an example over here, that is 4 and 8, and if we add these two numbers, the result is 12. The 12 is not represented in BC directly. So if we add these two number in the binary form, we can get 1100. This is not a valid BCD number. So how we can convert this number into BCD number? By adding a binary 6, that is 0110. So the thing is that why we are adding only 6 in this? Why we do not add 5 or something else? So the reason is that we are with the help of 4 bits, we are able to represent up to the number 1, 1, 1 and 1. But in the BCD, we are only representing up to 9, that is 0, 1, 0, 0, 1. So if we add 6 in this, we get the maximum value, that is 111, and after this 1 bit is extended and the series is start repeating itself. So as we can see over here, this is the number that is greater than 9. So if you want to convert this number into the sum that is less than 15, or that is in the range of from 0 to 9, we have to add 6. As we can see over here, we have to add 6. So the number is again come into the range from 0 to 9 only, this 4-bit number, and one extra bit is added, which is again became 4-bit equivalent by using extra 0 in front of the extra bit. So this number is converted into 1 and 2, that is equivalent to 12, which is the sum of two 4-bit number 1 and 2. So just by adding 6, this is known as the error correction, and when this correct this error by adding 6, we get the decimal equivalent of the addition 4 and 6. So there is no need of any correction over here if the result is less than 9. There is a need of correction when the result is greater than 9, as we can see over here. And the third case is when the sum of the two decimal number is greater than 9 and there is a carry as well. Like the sum is less than 9 but there is a carry as well. Like in this case, if we add these two number 8 and 9, then 17, this is 7 and there is a carry 1 and this carry is over here. So if the sum is less than 9, as we can see over here, the 7 is less than 9 but there is a carry term over here. So if this is the case, then again we have to add the BCD 6 in the number so that we can again come into the range from 0 to 9, and there is and we can easily represent this number in the BCD format. So as we add, this is the addition of 100 and 1001, 8 and 9, we have 10000 and 1. Now we can add binary 6 over here, then the number is 10000 and 1. Now in this case, if we see the 4-bit equivalent, this is equal to 7 and there is a carry which is converted into the 4-bit equivalent by adding extra zeros, and this is we get, that is 1. So the total sum is 17. So in this way we can convert any BCD number. We can add any two BCD numbers by considering these cases: when the sum is less than 9, when the sum is greater than 9, there is a correction of addition of binary 6, and when the sum is less than 9 but there is a carry, then again in this case we have to do the correction by adding binary 6 in the number. So in this way, we can perform the BCD addition in the BCD numbers. So BCD is nothing but the 4-bit equivalent of the decimal number from 0 to 9. In case of BCD addition, we have to perform some error correction when the case lies between these two cases. So in this way, we can deal with the BCD numbers. The next code is the other binary codes. There are many binary codes that is already exist. That is, the digit is from 0 to 9 and its binary equivalent is like this: BCD, as we can already see, 8421 code. 8421 is nothing but the weight assigned to the each binary bit. Like if we see this one, that is fifth, that is 0101. So the weight of this bit is 2 to the power 0. The weight of this bit is 2 to the power 1. The weight of this bit is 2 to the power 2, and this is 2 to the power again 3. So if this bit is 1, it is represented as 2 to the power 2, 4, and this is 2 to the power 0, that is 1, because these are having 1 in this place. So the sum is 5. So this is the binary code. This is the binary code of decimal number 5. So these 8421 is the weight assigned to the different binary locations in this code. That's why it is known as 8421 code. Similarly, there is again a 2421 code also exists, in which the weight of the highest, most significant bit is only 2, not 2 to the power 3. So in this case, if we want to represent this number 1011, this is 2 to the power 0, 2 to the power 1, 2 to the power 2, and again this is only 2. So we can write this is 2, this is 2, and this is 1. So this is equal to 2 plus 2 plus 1, that is 5. So we can represent 5 is in 2421 code by this number 1011 only, as you can see over here. So if the code is 2421, there is a bit pattern, there is different from the 8421 due to the weight assigned to the number. Axis 3 code, this is again a special decimal code in which there is an axis of 3 in the decimal equivalent number. Like if we have the binary number this, and if we add this, this is the binary equivalent of 0, and this, if we add 3 in this number, then we find that is equal to 0011. So the binary code in axis 3 of 0 is equal to 00 and 11. So in this case, for the 0 it is 0011, for the 1 it is 0100. So in this case, in the 1 we add binary 3, and this became 1 plus 1, 0 carry 1, 0 carry 1, this became 4. So this is equivalent to 4 over here. Similarly, there is a axis of 3 in each digit from 0 to 9. Like for the code, this is almost equivalent to 12, as there is a addition of 3 in this. There is another type of binary code exists, that is 84 minus 2 minus 1 code, in which the weight assigned to the last 2 bits is in the minus. That is, we have to subtract these bits in the total summation of all the bits if there is a 1 in that places. Like if we consider this number 0111. So if the code is 84 minus 2 minus 1, so we have 4 over here, minus 2 and minus 1, that is equal to 1. So the binary code of 1 in 84 minus 1 minus 2 minus 1 code is equal to 0110. So in this way, we can represent all the number from 0 to 9 in 8421 as well by according to the weight assigned to these numbers. So these are the different codes. Some bit combination are not used in the given different codes. Like for the BCD, there is no 10, 11, 12, 13 code exist. These are not binary codes, and these combination are not used. In this case, these combinations are not used. In this case, these all combinations are not used, and in 84-2-1 code there is no use of these kind of combination. So these are the different binary code that we can use in different applications of decimal numbers. Now next is gray code. Gray code is a special code in which there is a 1 bit difference in each code. That is, if we see over here, there is a code of 0 and there is a code of 1. 0, 0, 0 and 0 and 0, 0, 0 and 1. So all the 3 bits are same. The only different bit is 0 to 1. So if we check the 2 consecutive bits in the gray code, you can see there is this pattern is always follows. Like if we see over here, the binary code of 6 and 7, 0, 1, 0, 0 and 1, 1, 0, 0. Again we see this bit is same, this bit is same, this bit is same, and there is only 1 bit difference. So in the gray code we see, if we have the 2 consecutive gray codes, there is only 1 bit difference from one code to the another code. So this kind of code is known as gray code. So we can convert any number to the gray code by like any binary number, like this binary number, into the gray code just by using the property of XOR gate. So the first bit is as it is, and if we do the XORing operation between 1 and 0 XOR, and for the different it is 1, we can write 1 over here. For the same bit it is 0, for the same bit it is 0, and for the different bit it is 1. So this is the gray equivalent of the binary code this. So in this way we can easily represent the decimal number to the binary codes. The reverse is also possible. Like if we want to convert this gray code to the binary code, write first bit as it is and do the XOR again between these 2 consecutive bits. Like for 1 1 it became 0, for 1 0 it has became 1, for 0 0 it became again 0, and this became again 1. So you can see this is again converted into the binary. So in this way we can convert the gray code to the binary and binary to the gray as well. Another is the ASCII code. This is the standard code for the information interchange and is named as American Standard Codes for Information Interchange. So these are the bit combination, 7-bit combination to represent different symbols that is used in the general communication language. Like for capital A, the code, the 7-bit code of the capital A is 0. That is 1 0 0 0 0 0 5 0 and 1. This is the fixed code for the capital A, and whenever you type A in any test, the binary this A is converted into this equivalent ASCII code, and this code is saved into the into your system, not this symbol A. So for the symbol B, this is again some code C, D and up to A to Z. Then from small a to small z, and for all the decimal number from 0 to 9, and special numbers like string, hashtag, asterisk. There is a code for each and every symbol that is written in the text. So these are the combination of 7-bit code that is already assigned to a specific symbols, and for the communication we can use these ASCII code for transfer the data from one place to another. So there are 94 such kind of symbol which is having a 7-bit code, ASCII code, and 34 non-printable symbols, non-printing characters like backspace, like space bar. In this, these are not printed. So these are, and again the code is assigned to this. So 34 such symbols are there which is not assigning, which is not printed but having a ASCII code in this ASCII table. So these are the example of some non-printable codes here and here. Now this is the standard ASCII table in which you can see how the code is represented in the different language, in the different test. Like for capital A, the most significant bit is 1 0 0 and the least significant bit is 0, 0, 0 and 1. So this is the code of capital A in this ASCII table. Then you can find the code for small e in this ASCII table. Like for highest bit, this is 110, and for lower bit, this is 0101. So this is the ASCII code for small e symbol that is used in the different test. So in this way, these all are the printable and non-printable symbol and their ASCII codes. Another is your error detection and correction codes. In error detection and correction code, we can like when we transfer the data from one place to another, there is a communication channel, and there is a lot of signal that disturb this communication channel. Like in wireless channel, there is certain frequency that is absorbed by the communicating medium, and it disturb the data transfer between from source to destination. Similarly, in optical fiber, there is multiple optical frequency that interfere with the data transfer, and few bit like 1 became 0 and 0 became 1. Similarly, in another transmitting medium, there is multiple noises that is introduced and create the different errors. Like if we want to transfer a data from from one place to another, but due to the external interference, let's suppose this 0 became 1. So in this case, how we can find this error and how we can correct this error is known as error detecting and correcting code. There is certain method in which, with the help of these like humming codes, is one of the method in which we can use this error detecting method and correcting method. So for that, we use a special parity bits between the main message bit to find out which bit is having a error and how we can going to correct this. Like for the even parity, we maintain the number of 1 even in the symbol, and for odd parity, we try to maintain the number of 1 in the odd number of 1 in the given code by adding some extra parity bits. So as you can see over here, this is only 1, 2, 3 and 4, that is even parity over here, and for this there is an odd parity of this. So by using different humming codes, this error detecting and correcting code can be easily find out. So this is all for today's lecture. In this lecture, we go through the BCD codes, decimal codes, ASCII codes, and error detecting, and then little introduction of error detecting and correcting code. Thank you.